4. So we have quite a busy session. We have 7 talks, and each talk will be 15 plus 3 minutes. And I will give speakers a 3-minute warning, sound like that. Just a second. So sounding like that, okay? Okay, so participants are allowed to ask questions, give comments when the talk is finished. So just use your raise hand feature on your Zoom. So, okay, but if no questions, no comments right now, I think we can start. And the first speaker is Alberto Accardi, who will talk about inclusive jet and dynamical mass effects. So please go ahead, Alberto. And the floor is yours.
Thank you, Sasha. Can you hear me?
Yes.
Okay, very good. Can you see my slides and pointer?
Yes.
Very good. Then you are set to go.
Cool.
I would like to talk to you about an interesting connection between jets and dynamical mass generation in QCD, which you may suspect that there is some, but we, together with Andrea Signore, we found a quite interesting way, novel way to access it and to explore the dynamical mass generation in QCD. Let me start with a few references. The first 2 talks that I wrote indeed with Andrea contain a detail of what I'm talking today. In particular, the second one has a lot of technical detail, even more than you might want to see, and that I will, however, much of which I will leave out of today's presentation, which I will try to keep at a more general level and I hope inspirational to some extent. This work is also based and built upon things that I worked on with Alessandro Bacchetta and even earlier with Wei Chu. After a brief introduction, I will discuss this introduce a little more this idea of inclusive jets and how then these connect to hadronization and in particular to dynamical mass generation. At the end, I will discuss a few experimental experiments in which this mass generation can be actually observed. So there are also observable consequences of all the formalism that I will flash today. So let me start with a little bit of introduction. We know hadronic physics is epitomized by non-perturbative QCD effects, in particular by confinement that has 2 facets. One that we encounter when we want to study the parton structure of hadrons, in which we sort of study the static effects of confinement, even though we need dynamical probes of these, and we study the hadron to quark and gluon transition. Conversely, if we free a quark or a gluon or create a quark or a gluon in hard scattering, this needs to dress itself and become a hadron. So we see confinement at work in hadronization. We want to understand this for both conceptual reasons, but also practical reasons, because in the end it is hadrons that we observe in experiments and not the quark and partons that our Lagrangians describe explicitly. Now, as the quark dress itself, QCD dynamically generates the hadronic properties. And a way of mapping this process, the quark to hadron transition, is through a number of fragmentation functions and jet functions that describe this process of creation of hadrons out of the energy of containing in the underlying partonic final state following a Hart process. We have a few of these, and we have a familiar fragmentation function in which we'll just look at one hadron and nothing else. We can look at this just as a function of its longitudinal energy, or a fraction of its light cone momentum compared to the light cone momentum of the parent quark or gluon. Or we can also observe a little more detailed picture we can obtain if we also look at the transverse momentum generation in the hadronization process. And these are described by collinear fragmentation function or transverse momentum dependent fragmentation function, TMD, or TMDFF in brief. If at the other extreme, instead of looking at one pattern, we just look at a bunch of stuff that has a given virtuality, or rather invariant energy, and we can define inclusive jet functions. Inclusive in the sense that we do not observe a specific hadron. So this is the other extreme, perhaps the simplest thing that you can think of about to describe the transition from quarks to stuff, to hadron. But we can become more daring, and we can also more detailed, and we can also look at the hadron inside this jet, and then we get the fragmented jet functions. And lately there has been a very interesting proliferation of these mixed sort of objects in which we look at hadrons inside jets for all kind of purposes, and with many different results, theoretical results. It's a very interesting time in, for this business. Now, what I will focus on today, in particular, will be the connection between the collinear fragmentation functions and the inclusive jet functions that will lead us to a new sum rule, or a mass sum rule, that allows us to access a dynamical generation mass from a theoretical point of view, but also has observational consequences, as we will discuss. And also, I will discuss briefly the connection between these inclusive jet functions and the fragmenting jet functions, and also, of course, from the first line to the fourth line. And all this seems to hang together. So let's start, or before that, what generates the masses of particles and hadrons? Well, it's not the Higgs mechanism that only gives us the current core masses. Sort of the kinematics of mass generation. Well, the rest comes from a dynamical generation from from QCD. It's a dynamical generation of mass that has been addressed and can be addressed in many different ways. One example is a gap equation, or other non-perturbative method, that connects the mass of the hadron to the core condensate in QCD. One can have a look at the energy momentum tensor and even have a hadron mass decomposition analogous to the spin decomposition. And we will hear a lot about this, I think, just in the afternoon or tomorrow. Anyway, we will hear a lot about this. And finally, what I want to talk about today is this mass sum rule for fragmentation functions, which is a new feature and observable experimentally. Let me start by looking at these inclusive jets that perhaps are the least familiar of all the objects I mentioned. An inclusive jet collects part of the energy sensitive to the jet virtuality S, and it is composed of three elements. It can be theoretically decomposed in three elements. One is perturbative radiation, that is here depicted with wiggles, and is part of the large S component. Then we have a non-perturbative low S radiation depicted with dashed lines. And finally, there is a component which is due to the non-perturbative quark propagation, the fact that the quark, as it moves, dresses itself. It is this dressing that is today's focus of today's talk. But we will see a little bit of the connection with that. Now, if we dare to look inside the jet and look at the hadron, we've got these fragmenting jet functions in which we also measure, for example, the momentum function of this hadron. And so we have a sort of a decomposition of the jet in that sense. These two things are connected to each other, you can very well imagine, but formally it's not all that naive or simple to show that the inclusive jet function is related to the sum over all possible hadron production mechanism over all produced hadrons of the fragmenting jet function. And more precisely, you have a sum rule that takes the form that you can see here, where J is the sum over H, the integral was Z of this fragmenting jet function G. And so the jet is the inclusive jet is the inclusive limit of in-jet fragmentation. In a very analogous way, you can think about this jet propagator, this quark propagator, as the inclusive limit of a fragmentation correlator. These are correlators, they are matrices in Dirac space, and they are connected, as I showed with Andrea in these two papers, by a formula that looks like this one. We have the jet the quark correlator is multiplied by its momentum k mu is equal to the sum over all possible hadron productions cases of the fragmentation correlator multiplied by the momentum of the hadron. Now this can be done in several directions, in all the directions in space. So you can have you have let's say essentially a longitudinal and a transverse direction in which you can decompose this general sum rule, this master sum rule. But you can also project out the Dirac structure contained in the Xi and delta correlator. And if you do that, you can obtain on the right-hand side the fragmentation function, for example, and then you obtain on the left side the sum rule for this. For example, if we project with the gamma minus Dirac function, Dirac matrix, we obtain the unpolarized D1 and a sum rule for that one. We will see that one. The sum rule, which we all know the sum rule for D1, the momentum sum rule for D1, and also corresponds to the sum rule between the J inclusive jet function and the fragmenting jet function. However, this connection between the formalism that I studied with Andrea and the formalism of the inclusive jet function happens only at leading order. It happens at leading order and it is integrated over the jet virtuality S, which we do not have here. The jet virtuality is generated by the QCD radiation, which is the element that we have not yet addressed in our formula. So beyond leading order, we are not yet sure what will happen, but at leading order, there is this connection, which is tantalizing because it gives us at least a heuristic way of imagining some rules also for the polarized sector of the jet function, for polarized jet function. Now, what we do new here, we go beyond the well-known sum rule for D1. We do all possible projections in all possible Lorentz directions, and up to twist 3, and we obtain a plethora of sum rules, some of which are simply give a 0 due to symmetry, and some of those, however, are interesting. And I will focus now on the sum rule for D1, and what we will see is the sum rule for the E fragmentation function. So what is this E fragmentation function? Well, there are many fragmentation functions. We have some rules for all of these, in fact, except the ones that go to 0 and after integration over the transverse momentum. But we have a lot of sum rules that you can find in our papers. So if I look at the hadronization, the fragmentation correlators, you can separate and expand it in several Dirac structures, and the coefficients in front of these Dirac structures are the fragmentation functions. There is a lot depending on the polarization of the hadron and the polarization of the quark, and a twist 2, which means the correlation between a quark and an anti-quark field that are generating later on a hadron H. We have 8 fragmentation functions, of which I will focus on the unpolarized UU, the complete unpolarized one, which is the usual D fragmentation function. At twist 3, we can repeat the same thing here, and the same idea, and we obtain a lot of fragmentation functions, of which I only focus on the E fragmentation function that describes the transverse polarization of a quark inside the hadron, or the generation of an unpolarized hadron out of a transversely polarized quark. Now, how we proceed is by looking at the quark propagator that can be expressed or decomposed in terms of a spectral function. And we have two because this is a pair. We have the unpolarized, the chiral even rho 3 spectral function, and we have a chiral odd rho 1 spectral function that describes the masses of the generated hadrons. If you project these with the gamma minus and the identity function, we obtain this famous sum rule for D1 and a new sum rule for the E function. So at twist 2, the unpolarized one sums up to 1, which sounds trivial. In fact, it's not, because it's due to the generic properties of the commutation relation, canonical commutation relations with quantum field theory.
Second signal, so it means time is over. So
I thought we were giving 3 minutes with the time signal.
And first signal was gone, and you didn't hear it, I think, right?
No, I didn't.
Okay, yeah.
Well, let me take 1 minute. The second one is a sum rule for this E function that sums up not to 1, is not constrained by any generic property of quantum field theory or symmetries, and sum up to a mass of the stuff that is produced, to a mass scale. And this mass scale, in fact, it can be further decomposed into a quark, a current mass MQ, and some mass that is dynamical generated by the correlation between the quarks and the gluons inside the hadron. And all the hadrons, because we are summing over all of this. And therefore, by summing up this E fragmentation function, the twist 3 fragmentation function, we can isolate the mass that is dynamically generated by QCD, which is extremely interesting. However, this is not only theoretical, but also contributes to physical observables. In particular, you can find it as a coupling between this mass and the transversality function in inclusive DIS. This is a contribution to the G2 structure of functions, or in semi-inclusive annihilation in polarized positron-electron scattering, that either produce, and we need a double spin asymmetry, either you need for example, a self-polarizing hadron like a lambda particle, or we can use the relative momentum to build our symmetry between two hadrons. So we look at dihedron, chiral odd dihedron structure fragmentation function. So as I try to convince you, we can access part of the dynamical generation of mass, as an aspect of the dynamical generation of mass in QCD from a theoretical and from an observational point of view. And this is quite a new and exciting thing that Andrea and I are studying these days. Thank you.
Thank you very much, Alberto. So we have 1-2 minutes for questions. So please raise your hand if you have any questions or comments. So far, I see nothing. Okay, a few more seconds. If people may come up to any questions. Okay, since no questions, thanks again. Thank you very much. Yeah, and the next speaker is Maria Zurek, who will talk about longitudinal double spin asymmetry of inclusive jet and dijet production at star. So, Maria?
Yes, yes.
Screen, please, and go.
I'm sharing my screen. If you can just confirm that you can hear me and see my slides, it would be awesome.
Yes, everything is okay. Please
Thank
go.
you so much, Alexander, and I am starting. So good morning, everyone. My name is Maria Zurek, and today I would like to tell you about our recent measurements from STAR for longitudinal double spin asymmetries of inclusive jets and dijets. So I will start with a few words of motivation and the experimental setting, and then I would show you the impact of our 2009 data, then bring 2 slides of the experimental techniques, and in the end I will show you our new recent measurements from data at 200 and 510 GeV. So studying the internal structure of the proton is at the heart of studying QCD in the regime when quarks and gluons are interacting so strongly that they are confined in hadrons. And at STAR, we use polarized proton-proton collisions to look at the especially spin structure of the proton in terms of its constituent quarks and gluons. And one question we ask is, how do gluon spins contribute to the proton spin? So to answer this question, we are interested to look in the gluon helicity distribution, which encodes to what extent gluons have spins aligned with the longitudinal polarized proton as a function of the proton momentum fraction, which is carried by these gluons at the particular scale. So to get access to the polarized proton-proton collisions, we use relativistic heavy ion collider, which gives us access both to the transversely and longitudinally polarized proton-proton collisions at the center of mass, energy between 62 and 510 GeV with alternating spin configurations bunch by bunch, and also spin patterns field by field, which allows to study polarized hard scattering processes with good control of systematic effects. And the whole campaign of collecting polarized proton-proton data with RIG is summarized on this plot with different, the integrated luminosity for different data sets. And here I'm concentrating on the longitudinal runs, of course. And I will be referring to the data from 2009 and 15 collected at 200 GeV, as well as data from 2012 and 2013 collected at 510 GeV. So the portfolio of our experiment, solenoidal tracker at RIG, namely STAR, is presented on this slide, but since I'm talking about jets, we are mostly looking into information from the time projection chamber, which gives us tracking and vertex reconstruction, of course, together with magnetic field. The information from electromagnetic calorimeter in the central region up to 1 in eta and cap up to 2, as well as vertex position detector and 0-degree calorimeters, which give us information about relative luminosity and serves as minimum bias trigger. So the general characteristic of STAR, which is important for us, is its large acceptance, both in tracking and calorimetry, which makes it simply a good detector for measuring jets. And this is what we're interested in. So how actually we can get access to the gluon helicity distribution from the proton-proton collision? So at the proton-proton collider, we have leading order access to gluons, for example, through measurements of jets or dijets. And when you look at the different sub-processes which we are probing at the central jet production at RIG, we have sensitivity to quark-gluon and gluon-gluon interactions, which give us access to delta G in the polarized measurement. So we measured the double spin asymmetries, longitudinal double spin asymmetries of inclusive jets and dijets, which describe the difference in the cross-section for the 2 different orientation of the colliding beams for the helicities, namely anti-parallel and parallel, normalized to the total cross-section. And this is just a leading order illustration, but you see that there is the sensitivity to delta G to the polarized distribution functions, As well as here we have unpolarized distribution functions, which we can obtain from the global fit from DIS, and the perturbative part. So generally the evaluations for the ALL are done at the next to leading order, and to support this, we also compared this evaluation next to leading order with our cross-section measurements, and I would like to point you to the talk by Dmitry Kalinki, which will be talking about the measurements of cross-sections tomorrow in the parallel session. So the precision measurement of double spin asymmetry from 2009 data from STAR is presented on this plot. So here you can see the ALL, so the double spin asymmetry, as a function of parton jet PT for two different rapidity regions. We see that they are both positive. So these data included in the global fits, in the global analysis, provided evidence for the positive gluon polarization in the range of X between 0.05 and 0.2. And in this plot, you can see the helicity distribution functions from two theoretical collaborations, namely NNPDF and DSSB, which shows the impact of this data while included in the global fit. So for example, on this left-hand plot here, you can see that including jets really brings it to the positive delta G. And here you can see what's the integrated delta G over different region of X, and how much does it contribute in this region and at this Q square to the overall spin of the proton. So the integrated delta G in the two different regions, namely where we have data from 0.05 to 1, and the region when the data is very limited, or back then there was no data, namely between 0.01 and 0.5, is presented on this plot, which shows generally, first of all, the impact of the data from 2009, but also the need for the future investigations and future measurements. So in the low X range, when the uncertainty is generally very large, we can push our sensitivity, to a bit lower X from STAR, going to more forward rapidity or going to higher energies. But of course, these are near-term improvements from STAR, and the really deep insight will come from the future measurements at EIC at much lower X. For the higher X range, so this range above 5%, the further precision can be gained from the jets, further measurements of jets and neutral pion probes, for example, as well as complementary probes, like, for example, dijets. So let me tell right now a few words about our experimental method. So how do we reconstruct jets, how we measure jets, and how we reconstruct our double spin asymmetries. So at STAR, jets are reconstructed with anti-KT algorithm, and to correct the jets from the detector PT level to the parton PT, as well as correct for some small trigger biases and reconstruction inefficiencies. We are also, of course, generating jets, and here we use, it's of course a simulation based on TITIA and the Xi'an detector simulations with embedded zero bias data from the same period the data is collected. And we reconstruct jets on the three levels, namely detector, particle, and parton, to make these corrections. From the 2012 data, we are also using the jet by jet underlying event correction technique using the off-cone method. It was introduced at ALICE in this reference. And here you can see the typical values for the underlying event correction for 2015 data. So reconstructed jets are counted for all four different beam helicity configurations. So this is this N to calculate ALL. So the factor which is here describes our polarization, so polarization of the two beams, which was measured by the RIG polarimetry group. And you can see that, for example, in 2015, the polarization was of the order of 52.3% with the 1.6% uncertainty, or 56.5 with 1.7% uncertainty. And this was measured with the carbon target polarimeter normalized with the jet target polarimeter. And the last factor, which is here in this ALL, is R3, which tells us about our relative luminosity for all, different Helicity beam configurations. And this is calculated using the heat information from the vertex position detector. So these are like forward detectors at a star. And for 2015, it was calculated or extracted with the accuracy, of 0.5 10 to -4. So actually the uncertainty is quite similar to this, what was calculated what was extracted in 2009 data. So this is how we calculate ALL. And right now I am showing you our recent results from the 200 GeV longitudinal run from 2015. So jet and dijet ALL based on this largest 200 GeV data set will likely conclude the longitudinal program with jets at star at this energy. And here you can see ALL for inclusive jets as a function of parton jet xt, or I can think about it as PT. So the new recent data is green in comparison to 2009 data, and I'm also, which is blue, and I'm also showing the theory evaluations from NNPDF collaboration and DSSV, which do include 2009 data, but do not include 2015. So you can see that both data sets are consistent with each other. And 2015 data has smaller, first of all, has smaller statistical uncertainties, since we have here, thank you, a twice larger figure of merit. And we have also improved systematics, originating mostly with improved underlying event correction technique and better calibration of the central barrel for this data set. So while included in global fits, this data will significantly reduce uncertainty on the gluon helicity distribution for X higher than 5%. And dijet data, also extracted from the same data set, will further constrain the underlying partonic kinematics, namely the X dependence of delta G. So here you can see the results with the same color scheme as on the previous slide. So the new data are in green, and you can see what regions of X gluon is probed for two different topologies, so-called, of our event. So when you see that we have more symmetric topology, where we have one jet in the east side of the zero, one on the west side, the X is more symmetric for two jets, but it's also narrower than for inclusive jets. Therefore, we have better constraint on it. And for more asymmetric collisions, we are kind of, shifting towards a bit lower X. Okay, and here are the data or results from the higher energy measurements. So these are jets and dijets at 510. This result is published. It is based on the 2012 data set. So you can see the results in red from 2012 in comparison to 2009 data at 200 GeV. So higher S pushes sensitivity to lower X, down to 0.02 about. You can see which ranges we are probing here. And we can see that the results are consistent for both energies. And this is the result for dijets. So this was the first measurement in this higher energy, which I mentioned was published, and the further precision will come from 2013 data, which about 3.7, 3.5 higher statistics. We also have the preliminary results, which were presented already last year, end of last year, for the digits, but using the end cap in star, which pushes us to even lower x, I mean, up to about 0.01. And once again, the further precision will come from the 2013 data, but these are only preliminaries for now. Great, and this brings me to my summary. So, you know, with jets at star, we can get insight into the gluon polarization, to the gluon helicity distribution. 2009 data, while included in global fits, provided evidence for positive gluon polarization at x higher than 0.05. The new results on inclusive jets and dijets are coming from 2005. 2015 data set and 200 GeV, and this is the most precise 200 GeV data set, which will most likely conclude the longitudinal program with jets at 200 GeV at star. And the further insight into the gluon helicity distribution with lower x will come with the near time improvements from star, from 510 GeV, and the deep insight will come from the future measurements at EIC. Thank you so much.
Thank you, Maria, very much. So the data is really very interesting, and I am really looking forward to seeing the impact for delta G constraint. From this.
Yeah, it's great. I agree.
Okay, so I see Yuri.
Yes, thanks. I just have sort of maybe not directly a question to this analysis, but could you please give me a feeling? So the jets presumably are sensitive to both the gluon polarization and the quark polarization.
Yeah.
So how do they distinguish, right? So the fact that the jets give the evidence for delta G and cannot be accounted for only by delta Q, can you give me a feeling why?
I mean, when you look at the processes which we are probing at the particular x for our jets, you see what is the different contribution. So the gluons vastly dominate at the gluon. I mean, it's a leading order picture. Gluon dominates at low x. So there is the dependence simply on this, where at what x which processes contribute respectively. So this is taken into account. So we are, dominated in this region, but also quark gluons and gluon, and this is taken into account with in the global fits. So that's why this sensitivity to delta G. But it's true that there is also some part from the quark contribution, but this is mostly at the significantly higher PT.
When you say gluon, you mean the hard scattering?
Yeah, I'm talking here, of course. Yeah, this is.
But the gluons may come from quarks in the protons, right?
Yeah, they can. So then, yeah.
Okay, but that's included, of course, by the evaluation.
Yes.
Okay. All right. Thank you.
Thank you. More questions or comments? Okay, let me ask one question. So how much more data do we expect from STAR? And actually, second question, so do you plan to collect more data for delta G program? So STAR and DRIC are expected to run until 2025. So it means that we may get 1 or 2 more polarized proton runs. So does STAR have any plans to collect more data for delta G program?
Thank you for all the questions, and also thank you for the previous question. I didn't say that. So the status is following. We likely do not plan to collect more data in the future, more longitudinal data. The main focus will be rather towards the transverse polarization with the STAR forward upgrade. As you mentioned, 2022, and then in parallel to Phoenix, 2024, 2025. and concerning that if more data is coming, so this is all what we have for 200 GeV. So 2009, 2015, the largest data sets. There can be also some analysis with NCAP, which pushes it a bit, to the more forward region. However, the final, higher energy sample is the 2013 sample, which is currently, almost being released, in the sense that analysis is practically finished right now. It's just a collaboration review, etc. And this will conclude the program at 510 GeV. But as I said, for the future years, STAR concentrates or plans to concentrate, of course, mostly on the transversely polarized runs.
Okay, clear. Thank you. So last call for the questions. I see no. Thank you very much, Maria.
Thank you.
And let's move on. So next speaker is Zhongling Ji, who will talk about longitudinal double helicity asymmetry results from Phoenix.
Yeah.
Zhongling, just go ahead.
Sorry. Hello. Thank you very much for giving me this chance to present our work. Maria just talked about the ALL from JETS at STAR, and I will talk ALL at Phoenix from derived photon jet and the charged pion measurement. The motivation, one of the motivations is still to probe the gluon spin inside the proton. And this is also important to solve the proton spin puzzle originally raised at the DIS measurement. The direct photon is called the golden channel because this reason. So if we collide two polarized protons, and most of the direct photon, more than 80%, is produced by this quark gluon compound scattering to a direct photon. And we measure this ALL from this process. And for this photonic level process, it can be calculated by perturbative QCD. And this other part is depend on the polarized PDF for the quark, which is measured at the polarized DIS experiment, and the unpolarized quark and the gluon PDF, which can be measured at the unpolarized experiment. So from this measurement and the calculation and other measurements, we can extract the gluon spin delta G. The advantage of derived photon is there is a little fragmentation contributions to the derived photon production. So there is no jet unfolding and no hadronization fragmentation function to introduce more systematic uncertainties. And other channels to probe this include the jet and the charged pion production. So this jet quark gluon compound scattering can also, not compound scattering, quark gluon QCD scattering can also produce a jet, and can also produce a hadron, such as pi plus and pi minus. And this plot shows the photonic level processes contributions to the pi zero hadron. So we can say a lot of process is include the gluon. The advantage of the jet and the charged pion is they have larger statistics because they are all no photon, they are all is a QCD process, and they have a much larger coupling than QED. And also pi plus, pi minus are separated for U and D quarks. So different center of mass energy probe different built-in X region. For 200 JeV, it's mostly the a little bit higher X region, and for 510 JeV, it probes the lower X region. Previous rate data probe this 0.05 to 0.2 X region, and also Phoenix 510 jet pi 0 ARL confirms a non-zero delta G. And also we see a lot of star data imply a polarization of the gluon. This Phoenix derived photon jet and charged pion measurement can further constrain this integrated gluon spin uncertainty to shrink it to a smaller uncertainty. This is the Phoenix detector at the mid-rapidity. This eta coverage is 0.35 and the phi coverage is about pi coverage. And to measure photons, this EM-TEL, light scintillator, and light glass are the main detectors. To select the high energy particles at the EM-TEL, we use a EM-TEL trigger. DC is a drift chamber, which can measure charged particles. PC3 here is a paired chamber, which can matching the track and the cluster to reduce double counting in the jet measurement. And REACH is a Cherenkov detector, which can do a PID for the charged pions. Now I will switch to derived photon measurement. The derived photon can be produced by these 4 processes. First is QG compound scattering. Another is QQ bar annihilation, and also include small contributions from parton fragmentation to photon and quark prime drawdown. Most of more than 80% is produced by the first process. This is because we have much more gluon at this X range than the anti-quark. So it can really probe the gluon in the derived photon measurement. The main background comes from the hadron decays. Most are the pi 0, also include eta omega and eta prime. The measurement is first measure all the photons, then subtract those decay photons, then that's just the derived photon yield. To further reduce pi 0 and other hadron decay background and also the fragmentation contributions, we use an isolation cut for the derived photon. The isolation cut means this is if this is the signal particle we measure, we draw a cone around it. The cone size is 0.5, and we require other particle inside this cone. Some of their energy less than 10% of this photon energy. This means this photon had a very clean environment around it. We do this because if there is a fragmentation process, this quark had a fragmentation to a photon, and in this way, it also had other particles inside this cone, so it's hard to pass the isolation cut. The same as the prime drawdown case, it is also hard to pass. And if here is a hadron decay photon, is also come with a jet and usually rejected by the isolation cut. The derived photon cross section is showing here. We compared with the jet Fuchs calculations, and it consistent with jet Fuchs measurement. Jet Fuchs calculations. And in the left plot, we show the isolated over inclusive derived photon and pi 0 ratio. So these black points are isolated pi 0 over inclusive pi 0 ratio. So we can see the isolation cut reduce a lot of pi 0 background. And The isolated over inclusive derived photon is showing these red dots. This is the data, and this blue line is the ratio from PCA calculation. We can see PCA overestimate the data, but it's much better than the Jet-Fuchs prediction. This is because the Jet-Fuchs is only a platonic level generator, and it's overestimated the data a lot. Include multi-parton interaction and parton shower, such as in PCA, is important for the inclusive derived photon production and to get the correct ratio. This can constrain the unpolarized gluon PDF. For the gluon spin, we need the ALL, and we can see this our data consistent with DSSV14 calculation. This will be the first published derived photon ALL, and it will constrain the polarized gluon PDF delta G. Now I will switch to the jet measurement. To measure the jet, other than the BBC and the EMCal trigger to select the high energy particles, we also use a drift chamber to measure the charged particle, and also require it had a match with EMCal or PC3. The EMCal energy required cut larger than 1 JeV, and also the time of flight less than 10 nanoseconds. This can reduce the pi-up event because the luminosity in this run is very high, and also require the cluster thread matching to reduce double counting, and only keep the largest PK in each event for the jet. The algorithm is anti-KT. The unfolding is used Bayes iteration method implemented in rule unfold. The jet cross section is shown in the right figure, and the calculation are from unload calculation plus the log R with summation R is the jet cone size. Here is 0.3. The calculation is at platonic level, so it's overestimated the data. It means the multi-parton interaction and the parton shower and is important to include in the calculation. And also this overestimation in calculation also have similar observations in the CMS measurement for the small jet cone size in the anti-KT algorithm. The jet ALL is showing right here, and the Phoenix result is the black one, and the star 2012 result is the red one. They are Phoenix result here showing are consistent with DSSV14 calculation, and it will contribute to the polarized gluon PDF. Notice here that the uncertainty are correlated due to the unfolding. And now I will switch to the charged pion measurement. The charged pion selection first is the pre-selection rule for the energy over momentum range to ratio to be 0.2 to 0.8, and also require the logical OR of the EMCal triggers, and also require there is a matching track in drift chamber with the EMCal. The first three conditions is called good track cuts, and go to the black one, and the next one is the rich Cherenkov light should fire more than one photomultiplier, and this will give the right one. And we can see a bump here is just due to the rich heat. And last chart is EM shower probability, which means it's very unlikely to be a electromagnetic shower. So this is called the electron rejection charts, and further reject the electron background and make the shape to the blue one. And the charged pion background from the simulation, we can see most of them come from the green one, which is the electron background. And from the right plot, we can see this is why we use E over P cut from point 2 to point 8, because this had a dip for the electron background and had the highest signal to background ratio in this range. And the charged pion ALL is showing left for the PT for the PT at the horizontal axis. We can see it's consistent with the DSSV14 calculations. The right is the same measurement showing the XT at the horizontal axis. We can see the 510 data probe lower X range, and the 200 JAV data probe high X range. There is not enough statistics to separate pi plus and pi minus to decide which one is larger, which one is smaller, and decide their order. We need more statistics. And this goes to the summary, and the gluon spin is important for us to understand the proton spin composition, and also to understand the proton spin puzzle. Derived photons' advantage is rate of fragmentation contributions, but limited by statistics. And jet and charged pion, due to their leading order process is a pure QCD process, so they have larger statistics, but they have a systematic uncertainty from unfolding or hadron fragmentation function. Charged pion measurement can also separate the up and down quark contributions. All of this with the forward cluster and the forward or central rapidity eta measurement can contribute to further global analysis to constrain the gluon spin. Thank you very much.
Thank you, Zhongling. We have 1 or 2 minutes for questions. Okay, one last call. Looks like no questions. Okay, thank you, Zhongling, once again.
Thank you.
So let's move on. And the next speaker is Yiyu Zhou, who will take about constraining gluon momentum and spin distributions from jet observables. Please go ahead. And the timer is on.
Okay, hello. Do you hear me?
Yes.
Okay, do you see my screen, my presentation?
Yes.
Okay, great. Thanks, Alexander. This is Yiyu Zhou from College of William Mary, and I work with Nabu Sato and Wally Melnichuk from the Jefferson Lab Angular Momentum Collaboration, which is also known as JAM. My topic today is gluon helicity distributions in protons. Okay, so motivation. Of course, we want to understand this proton spin puzzle, which we know that the quark the quark spin does not account for all of the proton spin. So we want to understand the other parts that could contribute. For the spin of the gluon, we have to access it with the pattern distribution functions. And for the angular momentum, we have to access the TMDs and GPDs. And the topic today is going to be focused on the PDFs. Okay, so how do we access the PDFs? The PDFs are known for its non-perturbative nature. So we have to extract those from the experimental data. And the basis of this extraction is first, the factorization theorem, which factorizes the PDFs from the perturbatively calculable part, and also the universality, which tells us that the PDFs appear in this, in DIS are the same as those in Dradian and jets. Okay, so before we have before we extract, we have to parameterize. So given this parameterization, how do we characterize how well this parameterization is? Well, we use a Bayesian inference, which tells us basically with a prior belief of a set of parameters, we can update our belief on this prior distribution given the new data by using a likelihood function, which is defined by the chi-square. And the chi-square is defined as experimental minus theoretical square over uncorrelated uncertainty square. And of course, in actual analysis, this has to take into account the correlated uncertainties and normalization, but this is just to give the idea. Okay, so we also, apart from the Bayesian inference, we also implement this multi-step strategy, which means we are not going to feed all the data into the filter at once. Instead, we start with DIS and then we add Dradian and jets. And at this point, we keep the unpolarized PDFs fixed. And then we add the polarized DIS and polarized jets to fit the polarized PDFs. And then at last step, we will release all the distributions and fit them simultaneously. Okay, so what are the challenges? The challenge is heavy computation, which comes from the 3,000 unpolarized data points, 400 polarized data points, 30 parameters to describe the unpolarized PDFs, 18 parameters for the polarized, and 24 normalization parameters. And plus that, we have to perform thousands of chi-square minimizations to just sample one posterior distribution. So this is a correlation plot for all the parameters, and me showing this plot is just to illustrate like how many parameters we have to fit. There are many parameters. So this tells us that a fast numerical computation is needed. And given the time limit, I'm not going to the details of this numerical implementation, but instead I'm going to jump right into why we are interested in jets. Okay, so unlike the DIS, the jet has a gluon sensitivity in its lowest order. So this makes the jet a very good probe for the gluon distributions. And not to mention that with only polarized DIS, we are not able to constrain the gluon truncated movements very well. Therefore, this brings us to the polarized jets. Okay, so the polarized jets, the observable called ALL, the double longitudinal spin asymmetry, it's introduced in previous talks. So I'm not going to spend much time on this, but one thing I want to point out is that the denominator of this asymmetry is nothing but the unpolarized spin, the spin average cross-section of jets. So this indicates us that maybe a simultaneous analysis is needed. Okay, so so here I'm showing the fits to the jets, and on the left is D0 round 2 data, and we can see we have a very good agreement of the theory with the data points, which are the dots here, across almost eight orders of magnitude. And we also include this the RIC unpolarized jet data for the very first time, and also with a very good agreement. Okay, so what are the PDFs? The PDFs, we have in general a good agreement with other groups, and yes, so that's PDFs. The focus of this talk, of course, is the polarized PDFs. So so here I'm showing the jet asymmetry fits. Plotted here is the arrow bars here are the experimental data and uncertainties, and the red bands, although it's hard to see in the first few plots, but the red bands are the theoretical, the theory predictions. So because we have in our Monte Carlo approach, we fit many replicas, so the theory prediction is a range rather than a central value. Okay, so we have a good chi-square, which means a good agreement with the data. Okay, so one thing that's good about doing this simultaneous fit is that we can extract the spin up and spin down distributions for the partons with a consistent treatment of the uncertainties. So here I'm showing up, down, strange, and gluon. So of course this strange here needs a little bit more of constraining, and that's our next step. But other than that, based on this current plot, we can see the up and down contributes relatively larger than the strange and gluon to the proton spin. Okay, so now I'd like to compare our results with the DSSV. So we know in 2014, DSSV claimed that there is an evident for the proton, for the gluon spin inside a proton by extracting a quote unquote positive gluon distribution, namely this red line plotted here. This is a mean, the average of their extraction, and the dashed lines are the 90% trust region. So, however, in our analysis, this quote unquote positive solution does exist, but also we find this this quote unquote negative solution, which describes the data just as well as a positive solution does. So here I'm showing the chi-square for the positive solution. We have a 0.9 overall chi-square, and the negative solution has a 0.91. Of course, this one, this trailing one here is not a evident whatsoever to eliminate this negative solution. So we want to understand why and how we have this negative solution. And turns out it all comes down to the theory assumptions. So in the past years, when it comes to the extraction of the polarized PDFs, the theory assumptions including the SU2, SU3 symmetries, and the PDF positivity are always almost always implemented. So PDF positivity, briefly, is a requirement that the magnitude of the polarized PDF should be smaller or equal to the corresponding unpolarized PDF across all X and for all flavors. So this all those theory assumptions are implemented because the relative large uncertainty that the polarized data experimental data have. So in order to extract a PDF that's not going everywhere, these theory assumptions are implemented. But keep in mind that by implementing more and more theory assumptions, you not only get more constraint, you also get more bias and less data driven. So we go ahead and test this SU2, SU3 and SU2, SU3 plus positively. So we go from implementing SU2 only to implementing SU2 and SU3 and ultimately SU2, SU3 and PDF positivity. Okay, so here is what we have here. Showing here the in the plot, the yellow is the gluon that we get by implementing only SU2 constraint. By the way, this all include polarized DIS and jets. Okay, so yellow is when you have SU2 only, and then we add SU3, where it is evident that these the uncertainties on the PDFs in the quote-unquote positive and negative region, they all shrink. So from yellow to the blue, and then we implement this positivity constraint, which as you can see, it is evident that not only in the positive region that the uncertainty in the high X shrinks, but also in the negative region, the negative solutions are gone. Okay, and looking at this red lines here, it matches what the DSSV found. Okay, so I also computed this gluon truncated movement from 0.05 to 1, which is also what the DSSV did. So as we can see, the quote-unquote positive and negative solutions, they contribute very differently to the proton spin, namely 0.2 and negative 0.5. So, and also going from SU2 to SU3, you shrink the uncertainty, and that's also reflected here in the plots. And going from SU3 to positivity as well, you get a truncated movement with a central value, and uncertainties almost exactly matches what the DSSV had. Okay, so in conclusion, the unpolarized jet data is well fitted, and the polarized jet data can constrain gluon helicity, but this gluon helicity depends largely on the theory assumptions. And also in the future, we are going to include cities for a consistent treatment of the delta S, the strange spin. And we are also going to look into AI that may help us improving the calculation speed and also reduce the memory used. And of course, we're looking forward to the ESA measurements. And thanks to my collaborators, Nabu Sato and Wally Melnichuk. And thanks to Chris and Patrick for helpful discussions. Thank you for your attention.
Thank you. Very good, very interesting talk. And I would expect questions. Yes, they are. So, Carla.
Hi, can you hear me?
Yep.
Yes.
Okay, I don't know, sorry if I don't know if I missed or not. What is the confidence level at which you present the uncertainties?
Oh, so in our case, we use a Monte Carlo approach. So we have many replicas, and we just have those replicas, and we compute the central value and uncertainties based on the replica.
Yeah, but I mean, for example, you show here the value of the truncated moment that is 0.21 plus or minus 0.03. What is that? I mean, it is 1 sigma, it is 2 sigma.
Oh yeah, sorry. Sorry. It's 1 sigma.
Okay, thanks.
Yep.
Thank you, Yuri.
Yeah, very nice talk. Just to understand actually the slide a little better. So I guess you're questioning SU2 and SU3 symmetries because they're not exact. So that's why you might want to relax them. But but the positivity constraint, if it's violated, that means the distribution, say, of helicity plus or helicity minus gluons should be negative, right? If both if both are positive, then the positivity constraint would be automatic. So yeah, but that would be a little bit strange, right? If a gluon distribution is negative for, say, helicity plus or helicity minus gluons. Can you comment what was the rationale for questioning this constraint?
Sure. So when there are no interactions, the PDFs can be interpreted as a number of photons inside a proton. But when there are interactions, this interpretation is no longer valid, and that's why we want to question this positivity constraint.
Which interactions, may I ask? Do you have in mind?
The interactions means that the proton scattering with either a proton or a photon.
Oh, but you have factorization theorem, right? So that you're using here. So that's just the theorem tells you that you have a gluon distribution contributing, and that's your gluon distribution. Why should it be negative? It's the same gluon distribution without any interaction, so to speak. It's just the correlation of F plus I, F plus J, epsilon ij, right?
Yeah, that question. Yeah, I have to think about it.
I mean, at small x, people go like beyond leading order, right? The NLO, maybe NNLO level. There, you may not have positivity of spin average, say, gluon PDF. And people argue that, to describe some of the features of the unpolarized gluon extraction at small x. But okay, anyway, yeah, I'll let other people ask.
Can I just say something?
Yep.
Just to answer the question, thanks, Yuri, for the question. So this is an NLO analysis. Everything here is at NLO. As far as I know, there is no QCD proof that PDFs beyond leading order have to be positive definite.
Yeah, that's what I was getting at. That's what really the question.
That's the simple answer.
Yeah,
okay, thank you very much. So next question is from Alessandra.
Thank you, Alexander. So it's similar to Yuri's question and Wally's comment. So first of all, I wanted to ask you, okay, maybe you don't want to impose necessarily positivity bounds, but why do you choose to do first SU2, then SU2, SU3, then the positivity? Can you try what happens just imposing positivity before the others? That's a first question. Secondly, it's true that in the NLO case, the positivity might be violated. However, in some observables you are using in the proton-proton case, you do have also leading order signals. And if you violate positivity bounds, I think you run the risk of having negative cross-sections at leading order.
Okay.
So I would also try to investigate more the validity of these positivity bounds.
Yeah. Thanks for the question. So first, for the first question, the positivity constraint is a much stronger constraint than the SU2 or SU3. So even if we do have tried the other order, which means we do not have SU3, but we have So without SU3 implement this positivity constraint, it gives almost exact same result as this current scenario is. So in short, that this positivity constraint is a very strong constraint in at least in extracting this this gluon. So I guess this might answer your question. The second, for the second question, we do have leading order and next leading order calculations, and the in the leading order, I think we did not violate this positivity, but in the next leading order, the next leading order calculations has to be cannot change the sign of the leading order calculation. Otherwise, it's not a next leading order. It's no longer a next leading order. So yeah, I guess this answer your question.
Okay, but I think
Yes,
you
yes.
need to go ahead. So thank you very much for your presentation, for very interesting questions. And I think the discussions will be going on in the future. Yeah, so let's move on. So we have the next speaker, Christopher Cocuzza, who will talk about simultaneous extraction of spin-dependent and spin-averaged PDFs from W production data.
Yes, thank you. So can you see my screen?
Yes, we can, and hear you very well.
Okay, so thank you for the introduction. My name is Chris Cocuzza, and I'll be showing the results of an analysis done in collaboration with the Jefferson Lab Angular Momentum Collaboration, JAM for short. So this is a simultaneous extraction of spin average and polarized PDFs, similar to what Yiyu just showed. But in this case, we'll be focused on W production, both unpolarized and polarized, and trying to extract the polarized light quark C asymmetry from that data. So before I begin, what is the JAM collaboration about in general, and what are their goals? So the goal is to understand the three-dimensional structure of nucleons through global QCD analyses, and to study quantum correlation functions such as parton distribution functions, fragmentation functions, etc. In the case of collinear distributions, we use collinear factorization in perturbative QCD to perform simultaneous determinations, for example, of spin averaged and helicity PDFs, but also other quantities such as pion fragmentation functions, etc. And we utilize Monte Carlo methods for Bayesian inference in order to achieve the most robust uncertainty quantification that we possibly can. So that was JAM in general, but this analysis in particular is focused on helicity PDFs. So we know that lots of research has already been put into the unpolarized C asymmetry, d bar minus u bar. So for example, there have been CQuest experiments in the past, or there are experiments at NuC in the past, and recently, just this year, there's been some new data from CQuest. However, I want to focus on the polarized C asymmetry, where much less is known. So there have been recent measurements on single spin asymmetries in polarized proton-proton collisions. And this is a plot from that paper where they, with a STAR collaboration, took the polarized PDFs from NNPDF and then did a reweighting with their new data to try to extract the polarized C asymmetry. And they found that the asymmetry is non-zero and positive. However, this was a reweighting, and so far this data has not been included in a true global QCD analysis until now. So this will be the first global QCD analysis of this polarized W production data from STAR, and we will also be performing a simultaneous extraction of spin averaged and helicity PDFs. So this is a global analysis, which means there are several different types of processes involved. So of course, there is a polarized deep inelastic scattering. And of course, there's going to be the W production data from STAR. And I am also including the polarized jet data that Yiyu just talked about. So going into more detail about all of that data, here it is displayed on the x q squared plane. So we have about 1,700 points from polarized deep inelastic scattering, all fixed target data. We have the polarized jet data, and we have the polarized W production data from STAR. So up here is the new STAR data. And down here, we have the Jefferson lab data, which I will get into at a later point. But for now, I want to talk about the STAR data. So we have this data. So how do we actually extract the PDFs from it? So let me give a brief summary of the JAM methodology. First, we parameterize the PDFs at a chosen input scale, in this case, the mass of the charm core, with a given parameterization. So for example, the one shown here. We then evolve the PDFs to a given scale using the DGLAP evolution equation. And once we've done that, we can compute all of the observables involved in this calculation. And then once we have done that, we can compute the chi-squared. We then determine the parameters, the most likely parameters, through Bayesian posterior sampling with a likelihood function that depends upon the chi-squared. And we repeat this process hundreds of times to get different sets of parameters. And each set of parameters we call a replica. So a few tricks that are done in the JAM collaboration is data resampling, which is where we generate pseudo data from the actual data by adding some random Gaussian noise that is weighted by the quadrature sum of the uncertainties to achieve more robust uncertainty quantifications. And we also, to help with the computational challenge, we use a multi-step strategy. So we start with the simplest case, which would be just deep inelastic scattering data and PDFs. And then in subsequent steps, we start adding more data, such as the W production or Drell-Yan in the unpolarized case. And we add more and more distributions as time goes on. Then in the end, we fit it all simultaneously, and those final parameters are taken as the final sample. So that's our methodology that allows us to fit all of this data. Here's just a sampling of some of the polarized DIS data that's included in this analysis. I don't want to go into too much detail here, but this is just showing some of the proton data on double spin asymmetries from DIS. And then here is some of the deuteron data as well. But what I really want to focus on is the single spin asymmetry from STAR. So here is the data from STAR, and the black line and yellow band shows our fit to that data. And so at leading order, the two observables, ALW plus or minus, can be written as such. And this shows that they are sensitive individually to the delta D bar and delta U bar. And this is what potentially allows us to extract the C asymmetry. So this observable is unique compared to all of the other observables in that it has polarized PDFs multiplied directly with unpolarized PDFs. And so a simultaneous analysis and extraction of both spin average and helicity PDFs is especially important for this observable. So we've tried fitting this observable with delta D with U bar equals D bar, so assuming no C asymmetry, and it turns out it's impossible. But breaking this assumption, we are able to fit the data, as you can see on this plot, and we find a chi-squared over a number of points of 0.5. And for the overall fit, including all of the other data, we find a chi-squared of 1.11. Illustrating that we are able to fit all of this data well. So with all of that data, what do the Helicity PDFs actually look like? So here I'm showing delta U plus, delta D plus, and the strange distribution. I'll leave the discussion of the gluon out since Yiyu just covered that in great detail. And I'll just focus on these. So I'm comparing here with JAM17, which was a simultaneous analysis of Helicity PDFs, pion fragmentation functions, and kaon fragmentation functions using semi-inclusive DIS and semi-inclusive annihilation. And in order to enforce or to impose SU2 and SU3, we take the values calculated from JAM17, and that is what we use to impose SU2 and SU3. And finally, there are no positivity constraints included in either of these analyses. So these are the polarized PDFs, but of course, what we're really interested in is the polarized C asymmetry. And so from JAM17, since it included a semi-inclusive DIS, in theory, that data is capable of distinguishing between the light C quarks. But from JAM17, it found that that data was in practice not capable of actually doing so. However, with the polarized W data included, we now find the red curve, which shows unambiguously that the asymmetry is 0 and positive below around x of 0.3. And also showing that it is the opposite sign of the unpolarized C asymmetry. And then another point I just want to point out is that thanks to the simultaneous nature of the extraction of spin averaged and Helicity PDFs, this allows for a consistent extraction of the quark polarizations. So by that, I mean the ratio of delta U plus and over U plus, or delta D plus over D plus. So since we are fitting both the numerator and the denominator simultaneously, this allows us to actually extract these quantities with robust uncertainty quantification. So that was what I had to talk about the C asymmetry. So let me talk briefly about the future. So going back to the XQ squared plot, I now want to focus on the high X data. So our plan is to use a so W squared here is the invariant mass of the outgoing particles in DIS. So our plan in the future is to use a low cut of 4G V squared. This was done in a previous JAM analysis, JAM15. And with this low cut, we're able to include high X data, which almost entirely comes from Jefferson Lab, which lives entirely in this region between those two cuts of 10 and 4. So this data is on proton, deuterium, and some of it is also on helium. And there's a lot of it. So with this high X data, in the JAM15 analysis, they use that high X data to extract higher twist effects, as well as, higher twist effects. So in the future, we want to add the jet data and the polarized W data and redo and improve upon the JAM15 analysis using the latest technology, data, and theory. So all of these results are from JAM15. So these are the higher twist corrections from JAM15. And then here is the quantity D2, which depends upon the twist 3 PDFs. And there is some new data coming out soon from JLab Hall A, which will provide data on D2 neutron. So in conclusion, this was the first global QCD analysis of the polarized W and polarized jet data from RIC within a simultaneous analysis of spin average and Helicity PDFs. This is the first confirmation from a global QCD analysis of a positive C asymmetry below around x of 0.3. In the future, we want to extend this analysis to study the high X Jefferson lab data and attempt to extract twist-3 PDFs and other higher twist effects. And we also want to improve upon JAM17 by doing a simultaneous extraction with pion and kaon fragmentation functions, which means including semi-inclusive DIS and semi-inclusive annihilation in our analysis as well. And finally, in the future, the EIC will obviously be extremely important for giving constraints on the Helicity PDFs, being the first polarized electron-hadron collider. Particular parity violating DIS could provide new information on the polarized strange distribution, which is something we still know very, very little about. And when it comes to nuclear effects, there's obviously going to be a lot of data coming from the JLab 12GV program that will help with that. And thank you to my collaborators, and thank you to Yiyu and Patrick as well.
Thank you very much, Christopher. So we have a few minutes for questions. Yes, Sandra, go ahead.
So it's a similar question to the previous speaker, Chris. So if you go back, can you go back to the slide with the, yeah, this one? No, the one with delta U plus over U. Yes, this one is. So first of all, do you confirm that if you were to impose positivity bounds, then these ratios have to be, should be between 1 and -1, am I right?
Yes, that's correct.
So this will impose a strong constraint at X above 0.5 or 0.7. Do you agree?
Yes.
Okay. So now the question is, okay, I agree that next to leading order, there is no strict requirement that the PDFs are positive. However, first, what happens if you try to do the leading order fit? And secondly, okay, maybe you don't fulfill positivity bounds, but at X equals 0.7, 0.8, you have something like 2, 3, 5, 10 times a violation of the positivity bound. Aren't you worried that this cannot be an alpha S effect? This is something that can spoil the positivity of the cross section.
So we haven't, unfortunately, I don't think we have done, or at least I have not done a leading order calculation of this, so I cannot speak on the results of that. But I believe the cross sections should not, I mean, we've extracted these values from the cross sections themselves, which are obviously positive. So I'm not sure why we would be concerned about that.
How much data do you have about above X equals 0.7?
Well, we have nothing.
Yeah, that's the point. So if you look there, if you simulate the cross section there, maybe you get something negative that you overlooked because you never had data there.
Right, right. So I would say above that region, it's essentially just extrapolation, and it's really hard to say anything in that region, which is why the error bands blow up to basically infinity.
Okay,
yeah, but in the regions of extrapolations is the place where you need theory constraints.
Right.
If there are good theory constraints, they are useful in the regions of extrapolations. Thank you.
Yeah.
Okay, next question from Carla.
Yeah, first maybe a comment following up what Alessandro said, and maybe it's a question also to the general audience. How much data do we have in that same region that you were talking about, Alessandro, about 0.5, 0.7 in X for unpolarized PDFs for the positivity bounds to really understand whether we are violating or not the positivity bound? And this is always a thing that I have in my mind. But a question to Chris, just a curiosity on slide, I don't know, and I think it's in the previous slide. One more. Okay, this one. The huge difference in the uncertainty for delta S plus, where does it come from? It's just different data or what?
Yeah, so the JAM17 analysis included semi-inclusive DIS and semi-inclusive annihilation. Well, semi-inclusive DIS is the relevant one, but so that does provide constraints on delta S.
Okay, thank you very much.
Okay, any more questions? Let me just give a comment. So for W, you used star data, very good, very precise data. And I would like just to mention that Phoenix has data within the rapidity close to 0, okay, but then in forward rapidity. For example, star data is limited by the rapidity about 1.2, right? So Phoenix moves to close to 2. Yes, but uncertainties are large, but as far as I remember, they show some tension with calculation. So what I would expect that they may have some the impact of it on the fit. So do you plan to play with the Phoenix data too?
Yes, so we have not implemented the Phoenix data as of yet, but it is definitely something we could look into in the future.
Okay. Thank you. So if no more questions and comments, let's move on.
I'll just comment briefly. I'm sorry,
yes.
just a very brief comment in response to Alessandro Bacchetta's comment. Alessandro, we never ever violate positivity of cross section. It never happens. So this question is kind of, and in regions where we don't have data, we don't have data. So, you know, the rest is speculation and extrapolation. But I mean, there's no issue as far as positivity of cross.
Okay, thank you for another comment. So let's move on. And the next speaker is Yossathorn Tawabutr, who will talk about helicity at small x LLA corrections.
All right, thank you. So can everyone hear me well?
Yes, we can hear you.
Okay, so I will
just
start sharing my screen. Okay. All right, and the slides are showing up fine, right?
Yes.
All right, so thank you for the opportunity for letting me to give a talk. My name is Josh Tawabutr, and today I will be talking about my work on the single logarithmic contribution to the helicity evolution at small x and for the quark. And this work is in collaboration with my advisor Yuri Kovshekov and Andrey Tarasov. So it has been known that the complete high energy picture of a proton not only contains its 3 valence quarks, but also the C quarks and gluons. And so the spin, which is a half of the proton, receives contribution from the spin and orbital angular momentum of all of its constituent particles. In this project, we are interested in finding the contribution coming from quark helicity, in particular the SQ. We know that SQ can be written as an integration over the Bjorken X of the flavor singlet quark helicity distribution, as written in equation 2. So the quark helicity distribution delta sigma can be measured experimentally, but only down to some minimum Bjorken X, which is larger than 0. Obviously, so in order to get the complete understanding of the quark helicity contribution, we would like to find the asymptotic form of delta sigma as x approaches 0. So at small x, which will contribute to which will complement the experimental result and give us the complete SQ. To do so, we we realized this relation at small Bjorken x, that the quark helicity distribution satisfies this integral of a quantity q, which depends, which is called the quark longitudinally polarized dipole amplitude. It depends on two transverse positions, x1 and x0, and a longitudinal momentum fraction z. And I will explain about what this means physically later. The integration is well over z, and the distance between the two transverse position, x1, 0, and the impact parameter, which is basically the midpoint between the two transverse positions. Now to explain in more details the quark polarized dipole amplitude, I want to first take a little step back and talk about the quark unpolarized dipole amplitude, which is represented by S10 as opposed to Q10 here, right? So S10 diagrammatically, we can think of it as a pair of quark and anti-quark moving in the minus light cone direction, and it comes in and interact with a target proton, which is moving in the plus light cone direction. In this talk and in our work, we represent the target proton in the shockwave formalism by just the blue rectangle, so there is no actual line, and the minus moving partons are represented by actual line. And when the lines here cross the blue rectangle, it is implied that some interaction generally takes place. Algebraically, the quark unpolarized dipole amplitude S10 can be written as in equation 4 here, where the V is the fundamental Wilson's line, and well, NC is the number of colors, and the angle brackets average over the wave function of the plus moving target proton. Now, moving on to the polarized dipole amplitude, it is a very similar concept, except for the fact that now, well, again, right, we have a quark dipole moving in the minus direction and a target proton in moving in the plus direction. But now we take the helicity dependent part of the interaction, which means it is sub-iconal. Here, for the sake of notation, we denote sigma to be the helicity of one of the quarks in the dipole. Oh, and by the way, when we say Q10, we tag on the helicity of the quark at the first number, at the first position. So in this case, the quark at x1, or anti-quark for the sake of argument. And diagrammatically, that line will be denoted by the gray square. So here, algebraically, we will have the expression in equation 5. Here, V1 polarized is not just the normal Wilson's line. It is what we call the polarized Wilson's line, which has a different operator expression. And another difference is the scaling. So because we are going sub-iconal here, at Born level, the tree-level cross-section is suppressed by the center of mass energy, which in this case is the momentum fraction z of the polarized quark times the center of mass energy square s. So when the Born level cross-section is suppressed, we decide to multiply. We have to multiply the bracket by zs in order to get an expression that goes as 1 at the Born level. Now, we can also define a similar quantity for gluon. So, well, it is the same concept, but now we have the gluon dipole, and again, the gluon at x1 has helicity lambda, and it interacts with the target proton in the helicity dependent fashion. And here, the operator expression is almost the same, except for the fact that now we have the adjoint polarized and unpolarized Wilson's line. Now, when we consider these quark and gluons polarized dipole amplitude, and if we think of the diagrammatic picture, if we consider the splitting of these quark or gluon polarized dipoles, if we consider the splitting that occur outside of the target proton shock wave, or diagrammatically outside of the blue rectangle, we can have several types of splitting, right? We can have the real splitting like shown here, and we can have some virtual splitting. We can have, you know, quark to quark and glue, or glue to quark and whatnot. If we include all those splittings and sum them up, we obtain an evolution of this form. So basically on the left-hand side, I write this to refer to the change in the dipole amplitude Q or G in the evolution term. So the change due to including these splittings. And to the first order in the coupling alpha S, we get all these kernel terms in the square bracket. So for each of the terms, we have the integration over the momentum fraction Z prime of the daughter parton. In this diagram, particularly, is a gluon, and the another integration, which is over the transverse separation between the daughter parton and between the daughter partons, basically. So if both transverse and longitudinal integral are logarithmic, then we call such the term double logarithmic, or DLA term, and the evolution generated by such the term, so by the splitting that gives such the term, the evolution will resum over alpha S log square of 1 over x. While if we consider the terms where only one of the two integrals is logarithmic, then these terms are single logarithmic, and we call them SLA for short, and they generated the evolution resumming alpha S log 1 over x. And these terms are subleading to the double log terms because at small x, right? Because when x is small, log 1 over x is big. Now, to look at the evolution in more detail, we consider a special case where the emission involved the emission of a soft parton only. And when doing that, in particular, what I mean soft, I mean longitudinally soft. So if you have the parent, in this case, the parent quark, but it can be a parent gluon as well, with if the parent has momentum fraction Z, and it splits a parton with momentum fraction Z prime, where Z prime is much less than Z. When this is the case, we are guaranteed that the longitudinal integral in the kernel is logarithmic. But for the transverse integral, we have to pick the proper subregion in the transverse phase space to get the logarithmic or non-logarithmic integral. So this means that the soft parton emission gives us a double logarithmic term and a type of single logarithmic term whose longitudinal integral is logarithmic. So for such terms, we call them SLAL, or single logarithmic longitudinal, for obvious reason. And when now if we discard all the single logarithmic term and keep only the double logarithmic terms, we get this evolution equation, which were derived in these papers. They look quite long here, but one thing that we should note is that the objects on the right hand side, which involves a lot of polarized and unpolarized Wilson's line, they are different. Like if we look at this term, for example, it's different from the object in the left-hand side, which means the evolution equation is not closed. Now given this, one may wonder how we can extract the asymptotic form of quark helicity from this, right? So the answer is to take the large NC, the large number of color, or the large NC and NF limit. The NC is a number of colors and F is a number of flavors. If we take either of these limits, the equations become closed and linear. For example, at large NC, the equation simply reduce to these, where G is the gluon polarized dipole amplitude, right? As defined earlier, and gamma is just an auxiliary function. So essentially, this is a system of equation one can, in principle, solve. at least numerically, right? And actually at large NC, the equation has been solved analytically, and at large NC and NF, it has been solved numerically, respectively in these papers. And the result is that the quark helicity distribution at large NC, it goes as a power of 1 over x, and at large NC and NF, it goes as a power of 1 over x as well, but it is multiplied by an oscillation term like so. So in both cases, the exponent of the power is close to this number. And another thing to note is that for the oscillatory pattern in the large NC and NF case, the period, which is inversely proportional to omega q here, is very large, and it decreases with NF. And by large, I mean the oscillation pattern will span a lot of like we span many units of rapidity. And that means you need to go to very small x to see like periods of oscillation. Another thing is there are phenomenological implications that were studied. And in this paper, I believe it is at large NC, and they will proceed on to the large NC and NF case. We want to improve the evolution equation even more by looking at the single logarithmic contribution as well. As a reminder, if you look at the soft parton emission, you get the double logarithmic terms and a type of single logarithmic terms, right? Now, if you look at hard parton emission, this gives us another family of single logarithmic terms. So in particular, if we have a parent parton with momentum fraction z and a daughter parton with momentum fraction z prime, if the daughter parton is longitudinally hard, I mean that both z prime and z minus z prime here are comparable to the parent's momentum fraction z. So as a result of this, the splitting term in the evolution equation will be non-logarithmic in longitudinal integral. And if we keep, as long as we keep this limit true, like so the separation between the daughter partons being much smaller than the separation of the parents, then the transverse integral will be logarithmic. And now we have a single logarithmic term whose transverse integral is logarithmic, or we call them SLAT. For such the term, another thing to note is that the factor in the z prime integral is coincide, like it's the polarized Dirac splitting function. Now, if we include all such the diagrams, like with hard. I'm sorry.
Time is over. Second signal was.
Okay, I will wrap up. I will wrap up. Sorry.
And try to go fast.
Yeah. So if we include all the double log and single log contributions, we will have these equations in terms of the Wilson's line, and the SLAT terms are written in blue. Here we know that we have to include the running coupling correction as evidence in, say, this term, for example, right? And because it is also single logarithmic. And now if we take the large NC and NF limit, the equations become closed, but as opposed to the double log case, it is nonlinear. So half of the large NC equation is shown here. So it is nonlinear because you need to include the evolution of unpolarized dipole here. So that is the result we have. And from here, we have the double logarithmic and single logarithmic evolution, and we have include, and that as a result of that, we have to include the unpolarized evolution and the running coupling. So as the next step, we will study into the connection between this equation and the polarized Dirac evolution, and we will find the numerical solutions to equation at this order for large NC and NF. And after that, phenomenological implications will be studied. So that is all for the talk, and I apologize if I went over.
Thank you very much. We have time for questions. I see Carla raised hand, but I'm not sure, is it for this talk or for previous one?
I'm sorry, I forgot to lower my hand.
Okay, okay. Any more questions or comments?
Then let me ask, I'm just curious. So has anybody ever tried to resum the single log given the build-up context?
Yeah, for Helicity distribution, as far as I know, I have not seen in the small x equation.
Well, not just okay. Okay. Very good.
Oh, sorry. Okay.
Okay, any more questions, comments, suggestions? Okay, thanks again. Thank you very much. We are slightly behind the schedule, but now we move to the last talk to be given by Andrey Tarasov, who will talk about the role of the actual anomaly in polarized DIS.
Okay. Can you see my slides?
Yes.
Okay,
well.
very good.
We hear you very well.
Okay, so thank you very much for this opportunity to present this work, which has been done in collaboration with Rajvin and Gopalan. So this result has been recently published and a couple of papers are in preparation. Let me see. Yep. So as we know that constituent quark model, it cannot explain the proton spin. So we know that contribution of quarks into the proton spin is relatively small, just about 30%. And so it's surprising, and that's what the spin puzzle is. And in this talk, I'm going to give our explanation to this phenomenon. And we know that, on these slides, you can see several definitions. So we know that the quark contribution into the proton spin is related to the first moment of the G1 structure function. And in the parton model, you can relate it also to quark helicity distribution functions. And if you substitute definition of quark distribution functions, you can find that the quark contribution into the proton spin is defined by the matrix element of the isosinglet axial vector current. So it's a matrix element of J mu5 current. That's what defined the quark contribution into the proton spin. And a non-trivial property of this current is, of course, that current is not conserved. So the non-conservation of this current is due to the presence of the triangle diagram. And if you write the triangle diagram, you calculate the diagram, and then you can take a divergence of this diagram, you can find that it's not zero, but it's defined by the trace of the FF dual combination. So that is a non-conserved current. And it actually has been argued quite some time ago that the presence of the anomaly leads to a very non-trivial physical consequences for the measurement of the quark contribution into the proton spin, and so which is a matrix which is defined by the matrix element of the axial vector current. But to see these non-trivial consequences, one should be careful in the calculation. So first of all, the very non-trivial but the crucial step is to consider the calculation of the triangle diagram not in the forward limit as we usually do in the standard PQCD approach, but do the non-forward calculation. So we assume that there is a certain incoming momentum L, which is a difference between vectors P and momentum P and Q in the triangle diagram. And what we need to do, we need to calculate this triangle diagram. And then after calculation, we can send the value of L to 0. And it is well known that if you do this calculation carefully, so you can find that the triangle diagram, it actually has a pole. So the structure of the triangle diagram is L mu divided by L squared. And it's proportional to the FF dual, which is kappa in this equation. And important thing is that this result is exact. So you get this result if you don't do any kind of approximations, you just exactly calculate the triangle diagram. and then you exactly reproduce the pole L mu divided by L squared. And interesting that the presence of this pole, it has never been addressed in the standard PQCD calculations. And that's because in the standard PQCD calculations, you assume that the triangle is essentially local. So you do your high energy expansion, you calculate your diagram using these high energy expansions. And then effectively you assume that the diagram is local, and then you never see this pole. At the same time, this pole structure is related to the fact that the triangle diagram is actually non-local, and the presence and the properties of the triangle diagram are related to the measure of the QCD path integral. So it's a non-local phenomena, and then as a result, you see the presence of the pole. So it's very non-trivial to see this pole in the standard PQCD calculations. And it was argued first by Jaffe and Manahar that if in the leading order calculation, which is the calculation of this triangle diagram, if you have this pole, so that means that this pole has to be regulated. So you cannot just have this pole because, I mean, it's divergence, right? So you have to take the limit of L going to 0. So then that means that there has to be a pseudoscalar contribution. So it's a non-perturbative contribution. But without this contribution, you cannot regulate the pole. You cannot get the finite answer result for your matrix element of J-mu5 axial vector current. And then there has to be a pseudoscalar non-perturbative contribution, which effectively regulate this pole in a way that the final result is finite. And then if you do this calculation, you can actually find that the quark contribution in the proton spin is defined by the F of dual contribution. So it's so first of all, this current is local, and the second important thing that it's manifestly gauge invariant, this combination. And of course, the non-trivial thing again is that the presence of this pole and the fact that this pole has to be canceled by the non-perturbative contribution is deeply related to the topological properties of QCD. The measure of the QCD path integral plays a central role here. And of course, all these cancellations can be described by the chiral word identity. But the key point is observation that the triangle diagram is not local. So as a result, the analysis of this pole structure is very different from, say, calculation of unpolarized observables where all your diagrams are effectively local. And what we do in our work, we generalize in particular this result to the G1 structure function. So what we do, we use a word-line formalism. Using this formalism, the essential point is that we start with the imaginary part of the QCD effective action, because the imaginary part of the QCD effective action, that's what is related, that is the part of the effective action which contain the anomaly effects. So we write a general form of the imaginary part of the QCD effective action in the word-line approach. So we have to extend our theory. We have to include non-perturbative coupling. So we have not only the standard vector couplings which we have in the QCD Lagrangian, but we have to extend the theory and add axial couplings as well. And then in this approach, we actually can calculate the triangle diagram. And doing this calculation, we explicitly reproduce the infrared pole of the triangle diagram. And in this sense, we for the first moment of G1 structure function, we reproduce these equations which has a pole, and we show that indeed the first moment of G1 structure function is defined by the operator F of dual. But then we can extend this calculation to the box diagram. Again, we start with the general representation of the box diagram. So we use a word line approach. So in this approach, we write down, it's a one loop exact expression for the box diagram. So in our calculation, we don't do any high energy expansion. We just calculate the diagram as it is, because it's we found that it's crucial for our calculation. And then we write down the most general exact form of the box diagram, and we do our calculation, and we find that the in the Bjorken limit, when q square goes to infinity and x Bjorken is fixed, we indeed can, in the box diagram, we find that the leading contribution is indeed defined by the triangle, by the infrared pole of the triangle diagram. So in this red box, you can see the pole, 1 over L squared, and then antisymmetric combination f of dual in the numerator. And then, since it's still a box, so we have some kinematical prefactor. And so in the end of the day, we find that the leading contribution into the G1 structure function in the Bjorken limit is defined by the infrared pole and also non-local f of dual operator. And interestingly, if we just take this equation and integrate over x Bjorken, we can find that the first moment is defined indeed by the local operator f of dual, and there's still a pole L mu divided by L squared. And we also did a similar calculation for the Regge limit, for the small x limit of QCD of DIS. And in this case, we assume that the interaction with the background field is effectively localized. So effectively, the leading order contribution is defined by sort of a triangle part of the box diagram, and we do a calculation. We reproduce the pole and we reproduce the FF2 combination. And formally, both results for G1 in the Bjorken limit and in the Regge limit, they are in agreement. So our conclusion that G1 is topological in both asymptotic limits of QCD. So so it's defined by the F of dual combination. And an important thing that we do an exact calculation. So we don't do any high energy expansion, but again, so from the point of a high energy expansion, this F of dual combination, it's a sub iconal correction. So to get this combination, one really have to go into a high order of corrections in the standard high energy expansion approach. So in this sense, the iconal expansion, it breaks down. So you have to go to the high order corrections and your high energy expansion. But we believe that so this result, so that G1 is proportional to F of dual, is really due to the fact that there is an infrared pole, and this infrared pole, it's really related to the to the topological properties of QCD. So it's related to the imaginary part of the effective action. So it's non-trivial how to use the high energy OPE for that part. And now, so the problem of measurement of G1 as a result, it's related to now can be formulated as the measurement of the matrix element of FF dual. And that's actually, we found that analysis has been done before. So in our approach, we more or less are in agreement with the conclusion. So it was done by Shore and Veneziana. And so what they found that when you measure or calculate the matrix element of FF dual or Q on this slide, so then they found that matrix element is defined by, first of all, topological susceptibility. That's the first term in this equation. And then there is a derivative term. And they found that it's just due to the chiral word identity. The first term is of order of 0, while the second term, it has a small but non-zero volume. And actually their prediction is that for the axial charge is in a good agreement with the Compass and Hermes data. So, and that prediction comes from this second term, which is a derivative of the topological susceptibility. So as a result, we see that so this approach we have, so it's very perspective, it's interesting, and it looks like it's indeed in the agreement with experimental data. But what we want to do in our approach is a worldline effective action. So we, and that's what our upcoming paper is about. So we really want to see how that pole, the infrared pole of the triangle diagram is canceled by the pseudoscalar contribution. And to do that, we start with the expression for the effective action. So as I said, the effective action, it has two pieces. It has a real piece and it has an imaginary part. And so imaginary part, it's really what defines the anomaly effects. So to see how the pole of the infrared anomaly is canceled, one really has to write down the most general form of the imaginary part of the effective action and see that calculation in that part. And so what we do, we write down that part, the most general part of the imaginary part, most general form of the imaginary part of the effective action WI. And then what we observe that indeed in the worldline Lagrangian, which contains coupling between pseudoscalar sector, between vector and axial vector coupling, there is indeed a contribution which generates Vesumin-Witten term, so which is a coupling of eta naught and FF duo, and that coupling effectively generates the derivative of the topological susceptibility, which defines essentially the quark contribution in the proton spin. And so we show how in this approach the chiral word identities are realized. And so in the end of the day, so what we find that effectively starting from this expression for the worldline effective action, one can look at the proton as a collection of quark of the world lines. And if the density of those objects is large, so then one can write down an effective action which define the G1. And so that's a form of the effective action that we propose. So it contains several terms. So in the second line, you can see the MV effective action. So that is going to define the unpolarized scattering. And in the second line, you can see the axial-like effective action. So it contains the coupling of FF duo and eta naught, and that coupling is essential for the cancellation of the infrared pole. And then in the first line, there is a certain distribution, which W, which define distribution of color charge rho, and also distribution of eta naught. And one can actually write down the form of this distribution and do the fitting of experimental data. So that's what we observe, and that's a summary. So we find that the anomaly appears in the infrared anomaly appears in both the Bjorken limit and the Regge limit. We find that the infrared pole appears in both limits, and the cancellation of this pole is it's due to the interplay between perturbative and non-perturbative sector. So we find that there is, after cancellation of the pole, the leading contribution to G1 structure function is defined by the derivative of the topological susceptibility. And we also introduce an effective action which satisfies this cancellation and satisfies the anomalous chiral word identity. And it actually contains two scales. So one is a saturation scale, and the second one is Yang-Mills topological susceptibility. And it's interesting, and we see it's very promising to see how that, so how So we actually can calculate the form of the G1 and actually get the prediction for EIC, and we think it's very interesting to look at the how that predicts the upcoming measurement of G1 at EIC. So yeah, thank you very much. That's it.
Thank you, Andrey. Okay, we still have maybe 1-2 minutes for questions, in spite that we are behind the schedule. Okay, Zhongling.
Yeah, I just curious that this gluon topological effect only existed at built-in x equals 0, or existed at finite built-in x, and can experiment measure it, or can does the lattice calculation of the gluon spin include this topological effect?
So, what we argue that actually this result, so it shouldn't, it's valid not only in the limit of small x. So because what we find that the infrared pole is essential for both Bjorken and Regge limit. So in this sense, this prediction is for the form of the sigma is valid in, well, in principle, yeah, for every values of x. Yeah, but I'm actually not aware. So I know that the people have tried to measure the topological susceptibility, but in this approach, it looks like one has to actually measure the derivative of topological susceptibility. So it's a more subtle, essentially, and also in terms of the lattice calculation. But as I understand it, it can be done. So I'm not aware about lattice calculation of the derivative of the topological susceptibility, but we believe that's what should be done to get the lattice prediction for the matrix element of the axial vector current.
Okay, thank you. So it's not a pure topological effect, right? If it's completely topological,
yeah,
it should only exist at x0. I think the pole should be canceled, and it doesn't have any physical meaning because it's just due to calculation. Anyhow, it should be canceled.
Well, it should be all x. It shouldn't depend on x, and especially here we're talking about the first moment, right, of G1. So the first moment of G1, it's solely defined by the triangle, right? And in the triangle, if you're doing an exact calculation of the triangle, you get the infrared pole. And as soon as you get the infrared pole, that means so your contribution, your J-mu5 matrix element of J-mu5, it's defined by the derivative of the topological susceptibility.
Okay, thank you.
Okay, thank you. More questions? More comments? Okay, thank you, Andrey, once again. And I think we are done for today. Thanks to all speakers, thanks to all who attended the session and who participated in the discussion. So the day is over. We have 2 more days. So see you or hear you tomorrow. Bye.